Hello class, in this video we will be covering limiting and excess reactants. Before I introduce and define what limiting and excess reactants are, I first want to help you recognize when you've got a stoichiometric problem that involves limiting and excess reactants. Whenever you're provided quantities such as mass for more than one reactant, then this is a problem which will involve limiting and excess reactants. If you can read the following example, this was the type of stoichiometric problem I first exposed you to in the previous video where the amount of one substance is given. However, when the question gives you amount of two or more reactants, then you're going to first identify the limiting and excess reactants before we can carry on with subsequent calculations. Let's unpack and define what is a limiting and excess reactant. The limiting reactant is the reactant that gets completely used up first in the chemical reaction. As a result, it is the reactant that determines or it limits the maximum amount of product that can be formed. This means that you are unable to form any more product because one of the chemical reactants have been completely used up first. Let's look at an example so you have a better understanding of what I mean by this. In the following image, I've got 5 sausages and 4 hot dog buns. To make a hot dog, you need 1 bun and 1 sausage. How many full hot dogs can I possibly make with the given starting materials? In this example, you can clearly see that you can only make 4 hot dogs and you've got only 1 sausage left over. Therefore, we say that the hot dog bun is a limiting reactant because it gets completely used up first and it determines the maximum amount of hot dogs that can be made, which in this case was 4. On the other hand, the leftover sausage is described as the excess reactant. Let's have a look at another example. I've got 6 slices of bread and 2 slices of cheese. If a cheese sandwich requires 2 slices of bread and 1 slice of cheese, how many cheese sandwiches can I make? In this example, I can only make 2 cheese sandwiches, but I will also have 2 slices of bread remaining. Thus, in this example, cheese is the limiting reactant and the bread slices is the excess reactant. Let's now see how we could do this using actual chemicals. To be able to find the limiting reactant, we need to make sure we follow the following steps. We need to ensure that we have a balanced chemical equation provided. If this isn't provided, then we will need to write a balanced chemical equation. Fortunately, in this example, the balanced chemical equation as well as the masses of the reactants are already provided. The second step is to calculate the number of moles of each reactant. To do this, I'm going to be using the formula moles equals to mass divided by molar mass. If I do this for both of the following reactants, I should get the following answers. The third step is to divide each amount by the respective coefficients. The coefficients of hydrogen is 2, whereas the coefficients of oxygen is 1. By performing this division operation, you should get the following answers. Step 4 reads, the lowest amount is the limiting reactant. Since 3.125 is the lower value, oxygen is the limiting reactant. Once we've established what the limiting reactant is, we use the mole ratios with the limiting reactant so we can find out what are the number of moles or mass of water vapor produced. Please note that if we were interested in finding the number of moles of water produced, we never use the moles from step 3. We must always use the number of moles or the value from step 2. This means that we use this value over here. However, you can see that in this example, it makes no difference because we divided the number of moles by 1, which doesn't change the value. However, if we had to divide this by a different value instead, in a different example, like 2, we still use this value over here for the mole ratios, not this value. Please make a note of this as this is a highly common mistake made by many students. Let's go through a couple of legitimate examples. This example reads 34.2 grams of propane reacted with 62 grams of oxygen in the following reaction. Part A wants us to find the limiting reactant. Since the balanced chemical equation has already been provided, I'm going to first calculate the number of moles of propane and oxygen by dividing their initial mass with their respective molar masses. To now work out which one is the limiting reactant, I'm going to divide the number of moles by their stoichiometric ratios, ultimately giving me these answers. The substance with the lowest number of moles is a limiting reactant, hence oxygen is a limiting reactant in this example. In part B, we are now going to calculate the number of moles of CO2 that will be produced. The amount of CO2 produced will be dependent on the limiting reactant, so I must perform mole ratios with oxygen gas. If we set up the mole ratios, it should look like this, where the ratio of CO2 to oxygen gas is 3 to 5. As I mentioned about a minute or 2 minutes ago, we must use the original number of moles of oxygen, not the one where we divided by its coefficient. Hence, we multiply 3 over 5 by 1.38 as opposed to 3.88. All that's left is to put these numbers into the calculator, but we need to make sure our answer is in 3 significant figures, hence the final answer should be 1.16 moles. In the next example, we've got a solution containing 0.6 grams of lead 2 nitrate added to a solution containing 2.60 grams of potassium iodide, and the balanced chemical equation has also been given. We begin by finding the limiting reactant by calculating the number of moles of each substance and then dividing them by their respective coefficients. Based on the numbers, we can see that lead 2 nitrate is a limiting reactant. In part B, we need to calculate the mass of precipitate formed, in other words, the mass of lead 2 iodide. To do this, we need to calculate the number of moles of lead 2 iodide formed by using the mole ratios with our limiting reactant, lead 2 nitrate. According to the equation, there's a 1-to-1 ratio, thus the number of moles of lead 2 iodide will be the same number of moles of lead 2 nitrate. From here, we can then calculate the mass by multiplying the compound's molar mass, and again, it must be expressed using 3 significant figures, therefore the final answer is 0.835 grams. It's time for you to check for your understanding. Pause the video now and give yourself 3 minutes to tackle this question. When you're done, resume again to check over your answers. Automatically, the first thing that we should be doing is to construct a balanced chemical equation. This is an example of a precipitation reaction because you've got 2 solutions forming a solid precipitate. The products of this reaction is aluminium hydroxide, and the other product will be sodium nitrate because we know that aluminium reacted with the hydroxide ion, so therefore sodium is going to pair up and react with the nitrate ion. Once we've established the products, we can then balance the chemical equation as shown below. Afterwards, we need to calculate the number of moles of each reactant. We can then work out what the limiting reactant is by dividing the number of moles by their stoichiometric coefficients. Based on the amounts, we can confirm that aluminium nitrate is a limiting reactant. We can then use mole ratios to work out what are the number of moles of aluminium hydroxide. According to the equation, there is a 1-to-1 ratio between aluminium hydroxide and aluminium nitrate, thus the moles are identical. Lastly, we can calculate the mass of the precipitate by multiplying by the molar mass of aluminium hydroxide, and when corrected to 3 significant figures, this will give us an answer of 9.15 grams. This is the final boss question. There's 5 parts to this question which goes up to E in your notes, so please give yourself at least 5 minutes to answer these questions. Resume the video again when you're ready to review your answers. Part A should be pretty simple for you at this stage. We first balance the number of carbons, so I'm going to add a 3 in front of carbon dioxide. Now we balance the number of hydrogens, so I'm going to add a 4 in front of water. And lastly, to balance the number of oxygens, I'm going to add a 5 in front of oxygen gas. In part B, we need to identify the limiting reactant. This is achieved by first calculating the number of moles of propane and oxygen present. The next step is to divide propane by 1 and oxygen by 5 as indicated by the balanced chemical equation. Based on these amounts, the limiting reactant is oxygen. Keep in mind for parts C, D, and E, we should always be using the original value of the moles of oxygen to do subsequent calculations. In part C, we need to calculate the number of moles of carbon dioxide produced. So we're going to use mole ratios with oxygen as our limiting reactant. The mole ratios of carbon dioxide to oxygen gas is 3 to 5, hence multiplying it by 0.1075 gives us an answer of 0.0645 moles of CO2 gas formed when corrected to 3 significant figures. In part D, we need to calculate the mass of water produced. The ratio of water to oxygen is 4 to 5, and multiplying that ratio by 0.1075 gives us the moles of water produced. From here, to calculate the mass, we multiply it by the mass of water, which is 18, giving us a final answer of 1.55 grams of water when corrected to 3 significant figures. For the last part, it's asking us to calculate the mass of propane that is left over or unreacted. To do this, we need to first find out what is the mass of propane that did react with oxygen and then subtract that with the amount we initially started off with. We begin by using mole ratios to find out what is the number of moles of propane that completely reacted with 0.1075 moles of oxygen. There's a 1 to 5 ratio between propane and oxygen, Hence, only 0.0215 moles of propane was used to completely react with oxygen. To find the number of moles of propane that didn't react, or the amount of propane that is in excess, we subtract the starting amount of propane, which we found at the beginning of the question, by the amount of propane that did react. This gives us an answer of 0.3149 moles of unreacted or excess propane. Finally, to calculate the mass of propane that is in excess, we multiply this answer by its molar mass, giving us an answer of 13.9 grams when corrected to 3 significant figures. I'll now like you to get further practice by answering the following questions. There's about 11 questions in total in the back of the worksheet, so have a go with doing them. Thank you for watching this video, and I hope to see you guys again in the next one. Bye.